Okay, hello everyone and welcome back to your YouTube channel. And welcome to this amazing video today. As you must be aware, I am recording this series of videos related to electromechanical conversion systems. And we have been working for a while with one of the magnificent and beautiful rotating machines. And that is the case of the direct current DC machines. And today I have a very exciting numerical example related to DC machine, and in this very specific case, today we are working with a shunt wound DC generator. So as you can see, let's start reading this amazing statement. A 10 kilowatt shunt wound DC generator having an armature circuit resistance of 0.75 ohms and a field resistance of 125 ohms generates a terminal voltage of 200 volts at full load. In other words, what I am telling you here is that basically this DC generator is producing 10 kilowatts when the voltage is 250. So there are a few questions over here. Determine A, the terminal current, of course, in amps. Second, the field current, of course, again in amps. Then the armature current in amps again. Then the copper losses at the armature winding in watts. Then the copper losses at the field winding in watts. And the copper losses in the DC generator, and we are talking about here the total copper losses, and that is again in watts. And finally, we have a very interesting question over here, the efficiency, and remember that we are using this Greek letter, and in this case the efficiency is in percentage, assuming that the iron friction and windage losses is 600 watts. So what I am telling you is that basically the losses for friction and windage and of course from the iron is 600 watt. Okay? So without further delay, let's start the solution of this very exciting problem. Okay? What I will do is just refresh you about basically the circuit model that we use for DC machine, okay? In this case, we are talking about a shunt DC generator. And basically in the DC generator, we have here the terminals, okay? And because this is a shunt machine, we have here the field winding, and over here we have the resistance in the field winding, and of course this is the direction for the current on the field winding. And here we have the beautiful armature, and this is the voltage induced, the MMF, the armature, okay? And because this is a generator, this is the input power, and this is a mechanical power, okay? So what I'm telling you is that this machine is producing this current. This current is divided here at this node, and some part of them is going to the field winding for excitation purposes, and the other part is going to the terminal because here we have an amazing load. So in this very specific case, we know that the resistance at the armature is 0.75 ohms. We know that the field winding has a resistance of 125 ohms. We know that the terminal voltage over here is 250 volts. And the load, in this case, the load is numerically equal to 10,000 watts. So Now it's very simple because when we know the circuit model, what we need to do is basically start to apply circuit analysis. And the first question is extremely simple because we have been asked about the terminal current. And the terminal current, if you remember, the terminal power is the terminal voltage multiplied by the terminal current. From there, we can extract the terminal current, and the terminal current will be power divided by voltage. In this case, 10,000 watts is the nominal power, and the nominal voltage is 250. So as a consequence, as you can see over here, the terminal current is only 40 amps. So for the next question, we have been asked about the field winding current. And the field winding current is extremely simple because as you can see over here from the circuit model, the voltage across the field winding is the same voltage across the terminal. So this resistor over here, 125 ohms, has a voltage between the terminals of 250. So what we need to do now is use the very amazing and beautiful Ohm's law. So Ohm's law say that the terminal voltage across the terminals of the field winding is equal to the field winding current multiplied by the field winding resistance. So from there, we extract the field winding current. So 250 volts coming from the terminals and the resistance 125 coming from the resistor. So we obtain here the amazing and a beautiful field winding current. And as you can see over here is 2 amps. But the next question is quite exciting because the next question is related to this amazing current over here. And this is the armature current. And the armature current, every one of my students, they can see that here we have on the right-hand side the armature current. Then we have here the field winding current. And finally, we have the terminal current. So if we apply Kirchhoff current law, well, you can see that the current going in is the armature current, and we have two currents going out, field winding plus the terminal current. So now we have an equation that is coming from Kirchhoff current law that we can use to calculate the amazing armature current. So the armature current coming from Kirchhoff current law will be the field winding that we already know is 2 amps, plus the armature current that is 40, and as expected, the armature current is 42 amps, and this is the answer C. So you can see over here that in this case, the armature current is larger than the terminal current. And there is no surprise over here because we are working with a shunt generator. In any shunt generator, you must remember that the current over here should be larger than here because there are some current that is going to the field winding for excitation purposes. So the next step is we want to obtain the efficiency, the total efficiency of this DC machine. However, there is something quite interesting over here, because we want the efficiency of this DC generator, and you must remember that is output power divided by the input power. However, if we think about the input power is basically the output plus the losses. So the output power is a data that is provided in the statement, because you must remember that the output power is 10,000 watts. That is simple, that is data coming from the statement. However, the interesting part here is related with these losses, because the total losses in the DC generator, we can divide these active power losses, these losses, into parts. one related to the copper, and that is basically all the losses related to power dissipation at the resistive component at the copper of every single winding in this machine. And the second part here is basically the data that we already know, because we know that the windage and the friction, the power, the total power is 600 watts, is coming from the statement. So now what we need to do is focus on calculating these amazing copper losses. But the copper losses, you can see that the copper losses, they are basically divided in two. Because we have only two resistors, dissipating energy in this very lovely DC machine. One power that is dissipated at the armature, and one power that is dissipated at the field winding. So starting from the armature, the power losses at the armature, they can be easily calculated because we already know the current, and we already know the value of the resistor. In other words, the armature loss is basically a square value of the current, 42, that we already calculated, and the resistant armature, that is 0.75. So this here, this number, 1,823 watts, represent the power losses at the armature. But in this case, we're talking about the copper losses at the armature, okay? Copper losses, and we use the letter Cu for representation. On the other hand, we have copper as well at the field winding. And again, the calculation is extremely simple because it will be the field winding current, the square value of that, multiplied by the field winding resistor. So as you can see over here, we have the field winding current, 2 amps, multiplied by the resistance, 125 ohms, and we obtain that the the field winding copper losses is 500 watts. So finally, as you can see over here, I am calculating the total copper losses, and that will be the sum of the armature copper losses, field winding losses. In terms of numerical, you can see over here, 1,323 watts plus 500, we obtain the total copper losses, 1,823 watts. So now we have all the numbers that we need to calculate the efficiency of this beautiful machine. Output power, 10,000 watts. And we have here at the denominator the total copper losses, that is 1,823, plus the losses associated with the with the iron and the friction and the windage, and that is a data coming from the statement 600. So from there we obtain a total here that is 2,423. So when we obtain the efficiency, voila, we obtain an efficiency that is probably not the highest in the case of a rotating machine, but the total efficiency is 80.5%. Again, it's not extremely high, but we complete our example here, or numerical example related to calculations on the shunt DC generator. Well, this is all for this video. I hope that you understand the explanation. It's extremely simple example. It's very straightforward, but you can use this kind of example for practicing all the calculations related with the DC generator in steady state. And over here, the main focus was related with the circuit model quantities and specifically to the power losses inside the DC generator. Well, this is all again for this video. I hope you enjoy. I hope you learn a lot from this video. And if you want to leave a comment, please feel free to drop an email or also a comment here in YouTube. And this is all for this video, and I will see you at the next one. Bye now.